Okay. And the last thing in section 2.2 is I want to talk about what I'm going to call the inverse function theorem for complex functions. So the inverse function theorem. And basically what this does is it gives us a formula for finding the derivative of the inverse. So before we talk about the inverse, there's just a little bit of background that I want to give. So a function, let's just call a function f going from g to h. So function f is going to be called 1-to-1, or sometimes called injective, if the only time that you get the same output is if you have the same input. So in other words, if f of a equals f of b implies a equals b, So for example, the function f of z equals z squared is not 1-to-1. So this is not 1-to-1. And the reason for that is that you can come up with two inputs that have the same output. So for example, f of I and f of minus I are both -1. But clearly I and minus I are different inputs. So here we have two inputs, but they have the same output. So that's not allowed if the function's 1-to-1. So a function's 1-to-1 if the only time you have the same two outputs is when you have the same input. So for example, if you were to have a linear function, like if you were to have f of z is, say, what's a good example here? Let's take I z. So what you do is you take the complex number z, and to compute f of z, you just multiply by I. This is 1-to-1, and in fact, it's 1-to-1 on the whole complex plane, and that's because if f of a equals f of b, then ai equals bi, and therefore a equals b, because you can divide both sides by I, everything's fine. So that forces a equals b. So functions with that property are called 1-to-1. A function f going from g to h is called onto if it has the following property. If for all values h and h, there exists, let me call it a b. For all values b and h, there exists a value a and g where f of a equals b. In other words, for every value in the codomain, it's got to be the image of some value in the domain. Okay, and if a function has that property, it's called onto. So, for example, if you were to talk about the function f mapping the complex plane to the complex plane given by f of z equals z squared, this function is onto. So f is onto, because every value in the complex plane is the square of some complex number. This is one of the first things that we proved in the first week. So pick some arbitrary value in the codomain. So pick, say, w and c. Then we've already seen that w equals z squared has a solution z. Okay, so in other words, every value in the codomain is the image of some value in the domain. Okay, and those functions are called onto. Another way to think about onto, f going from g to h is onto if the range of f, in other words, the set of images of f, the value f of x such that x is in g, if that's equal to the codomain, then the function is onto. Okay, and finally, f going from g to h is a bijection if it's 1-to-1 and onto. So if it is 1-to-1 and onto. There's a lot more that you can say about bijections, and there's many examples that I'm just kind of glossing over. I just want to do this very quickly. But it turns out that bijections are exactly the functions that have inverses. So if f going from g to h is a bijection, then f has an inverse. And the inverse is defined, well, first of all, it switches the role of domain and codomain. So the inverse of f maps h to g, and it's defined by f prime of h equals g. Let me say it this way. F prime of b equals a if and only if f of a equals b. Okay, and so it turns out that this is exactly the right conditions that you need in order for you to have a function that's an inverse. So just a little bit of background on when inverses exist. And then finally, the inverse function theorem talks about derivatives of inverse functions. So the inverse function theorem says the following. So the idea is suppose that f and g, suppose that f, maps g to h is a bijection. That means that then there's an inverse, and the inverse is going to have the following property. So if you look at f of f inverse of z naught, and you want to think about what's the derivative. I'm trying to, in math, things are always written slightly backwards. You do things ahead of time and then you write it nicely. Let me do it the right way to show you what I mean. So in other words, I'm going to go through the proof before I even tell you the result. This is how real math is done. So f of f inverse of z, if you take the derivative, well, f of f inverse of z is just z. That's what an inverse is. So that means that the derivative is going to be 1 on the one hand. On the other hand, if you take the derivative of f inverse of z, you just apply the chain rule. This is the derivative of f times f inverse of z times the derivative of f inverse of z. Okay, and so what this tells you is the following, and this is what the inverse function theorem really says, is that if you want to find the derivative of the inverse function of some function f at z equals z naught, say, this is going to be 1 over the derivative of f evaluated at f inverse of z naught, assuming, of course, that the quantity on the right in the denominator is non-zero. So assuming f prime of f inverse of z naught is not equal to 0. Okay, and so that is the inverse function theorem. Okay, the book has it written a little bit nicer, and it even walks through a more formal proof using limits, but this is the inverse function theorem.